Hello, welcome to our channel for probability and statistics. In this video, we will introduce goodness of fit test in statistics. So goodness of fit test is based on the idea that we want to know how good a fit we have from the data between the frequency of occurrence of observations, this is data, and the expected frequencies obtained from the hypothesis distribution. So we take a look at an example, a very simple example. So we consider the tossing of a die. So if we hypothesize that the die is honest, or say the die is fair for each side, so which is equivalent to testing the hypothesis that the distribution of outcomes is the discrete uniform distribution f(x) equals 1 of 6, where x can be 1, 2, 3, 4, 5, 6. So for each side, the die has 6 sides, right? For each side, there has the same frequency occurring. So say we get the data, suppose that the die is tossed 100 times, and we record the outcome. So theoretically, if the die is balanced, which means each side has the same probability to occur, then we would expect each phase to occur 20 times. So the result can be seen from the table. This is observed counts. We get the data, the total 100 times. And this is expected. So if the die is balanced, the size fair, so we can get 20 for each number. So by comparing the observed frequencies with the corresponding expected frequencies, so we must decide whether these discrepancies are likely to occur as a result of sampling fluctuations and the die is balanced, or whether the die is not honest and the distribution of outcomes is not uniform. So this means we get the sample. Of course, the sample will not necessarily be exactly the same as the expected value, right? Each sample will have random number. But we have to decide from the calculations that this random number from a die balanced or not balanced. So we have to get appropriate statistic from the sample and the expected value. We decide if we will hold the hypothesis that the die is fair or not, right? So this statistic can be got from observed value minus expected values and take square, then divided by the expected value. Then we take a sigma for odd fields in the table. So this statistic we call the chi-square. And this is a goodness of fit test statistic. And this value will follow approximately by a chi-square distribution with k-1 degrees of freedom. If the hypothesis of fair die is hold. So we calculate this table, some odd values from the table where this is difference between the expected and observed value, and take square divided by expected value. So we got this test statistic equals 1.7. And if If the die is fair, so this value will follow a chi-square distribution with 5 degrees of freedom. Next, we will take a chi-square test. So this is a chi-square distribution's density curve. And this value called critical value chi-square alpha, which means upon this value will lead the area to the right of this value under this curve is alpha. So in a chi-square test, alpha usually 0.05. Or say this critical value will leave the area very small to the right, about 0.05, because the total area is 1 under this curve. So 0.05 is very small. So if we get sample test statistic on the right side of this critical value, then we will say the test is significant and we will reject the hypothesis or reject the null hypothesis that the die is fair. If this value is located in the white area or not on the right side of this critical value, so we will say the test is not significant and we will hold the hypothesis that the die is fair. So from this sample data, chi-square value 1.7 and the chi-square for chi-square distribution critical value is 11.07 for 5 degrees of freedom. So you can see this sample statistics is much less than the critical value. So we fail to reject, or say we do not reject H0. So we will conclude that there is insufficient evidence to say that the die is not balanced. In other words, we will hold that the die is balanced. Thanks for watching.